5.3 Standard Deviation. In this section, we're going to be learning about a new term called standard deviation, but we need to be incorporating a term we are already familiar with called the mean. So to describe data numerically, we often use two numbers. The mean, which you've learned about in previous sections, which is the average, is represented in our equation by both x with a line over top of it, or this fancy u. Those two symbols are interchangeable, meaning you could write that in this section right here in your formula. You can either write the u or you can write the x with the line over top of it. It doesn't matter, as they both represent the exact same thing. The symbol that we're very new to is this crazy looking E, which represents sum, and the name of it is sigma. So as we're familiar with determining the mean, we know we need to add, so the sum, add all of our terms. X is just the data, and divide by n, which is the number of terms. We're not used to writing our formula out in this way, which you still don't have to, but that's what the symbols are describing to us. We need to use the sum, add our data terms, and divide by n, which is the number of terms. So the formula that's new to us is standard deviation down here. And we're going to break that apart so we know what all of the components mean. This first symbol here, it's almost like a O with a little loop through the top, means standard deviation. This E again we've seen means sum. Sigma means sum. Here's our X, that just means your data, the number you're talking about. Our U, we already talked about at the top, is mean, or your average. And I use, again, X with the line over top of it, more so than I would use the U. But you have the option there. And N is the number of terms. The smaller the standard deviation, the more consistent the results and the closer to the data is to the mean. So this means if I'm going to calculate a bunch of data, find the mean, I'm going to compare that number to see how far away it is from my average. And the closer that it is, that means my standard deviation will be a very low number. If my number is very far from my average, then my standard deviation will be a higher number. So we'll see that by a couple examples here to follow. So example 1. Calculate the standard deviation from the following sets of values. We have 5 terms here: 7, 8, 9, 10, and 11. Our first step we want to do is calculate the mean. So our mean for this set is the sum of all of our data, so 7 plus 8 plus 9 plus 10 plus 11, divided by the number of terms, which is 5. We get 45 divided by 5 equals 9. So 9 is our mean, our average. In our formula, using our formula, we need to take the square root of the sum of our deviations and divide it by the number of terms that we have. When I say deviation, deviation means how far apart that data term is from your mean. So let's look at 7, for instance. So it's just this bracket, your data minus the mean. That's like using 7 minus our average now, and that's -2. Means 7 is 2 away from 9, which it is. It's 2 less, so it's a -2 away from our average. So we need to incorporate that into our formula. So standard deviation equals the square root of, and we're going to add up all of our squared deviations. So 7 minus 9 squared. Again, I'm getting that from right here. Our data minus our average squared, and we want to add up all of them there. That's what sigma is telling us. So 7 minus 9 squared plus, we're finding the sum of 8 minus 9 squared plus 9 minus 9 squared plus 10 minus 9 squared plus 11 minus 9 squared. And please make sure that your square root sign goes over top of all of those values. And that's all divided by n, which is the number of terms, and in this example it is 5. Simplifying that further, 7 minus 9 is negative 2 squared plus negative 1 squared plus 0 squared plus 1 squared plus 2 squared. Again, finish off your square root sign. Still all divided by 5. Simplifying our terms underneath, negative 2 squared is 4, plus negative 1 squared is 1, plus 0, plus 1, plus 4, divided by 5. 4 plus 1 plus 1 plus 4 is 10. Square root of 10 over 5 is really the square root of 2, which is 1.41. So our standard deviation in this question is 1.41, which is fairly small. This tells us that our data numbers, our 7, 8, 9, 10, 11, must be fairly close to our mean of 9, which they are. They're only a couple numbers off each way. So again, a smaller standard deviation means we are more consistent, or the data is closer to the mean. Next example. The data we have here is 7, 9, 11, 13, and 15. Again, first step, determine what your mean is. What is the average of this data? So our mean is 7 plus 9 plus 11 plus 13 plus 15, all divided by the number of terms, which is 5 again. 7 plus 9 plus 11 plus 13 plus 15 divided by 5 gives us 11. So our average is 11. Standard deviation equals the square root of the sum of all of the deviations squared divided by the number of terms. So let's find our deviations. How far away is 7 from 11 squared? Plus, how far away is 9 from 11 squared? Plus 11 minus 11 squared, plus 13 minus 11 squared, plus 15 minus 11 squared. And then all divided by the number of terms, which is 5. Simplifying, square root, 7 minus 11 is negative 4 squared, plus negative 2 squared, plus 0 squared, plus 2 squared, plus 4 squared, divided by 5. (16) plus 4 plus 0 plus 4 plus 16 divided by 5 gives us the square root of 40 divided by 5, which is really the square root of 8, which gives us 2.83 as our standard deviation. So what we should see from here is, compared to our last example, this standard deviation is slightly higher than our first, which means our data, our numbers from the initial beginning of the question, should be more spread out from the mean, should be farther away from the mean on either side than our first example was. So 7 should be farther away from 11 than it was from 9, which it is. Okay, so the larger your standard deviation just means it's more spread out, the farther it is away from your mean or your average. Example 2. Calculate the standard deviation for the following sets of data. You'll notice in this table that on the left-hand column we're given a range of numbers. So the daily commute time for the employees is in between 0 and 10, in between 10 and 20, in between 20 and 30, 30 and 40, and 40 and 50. When you're given a range, leave a little note for yourself that you want to use the middle value. So if given a range, use your middle value of those numbers. So in this case, between 0 and 10, I'm going to use 5. Between 10 and 20 is 15, 25, 35, and 45. Those are the numbers we're going to be using for our data on the left-hand side. Our first step is always to find our average. So normally we would add 5 plus 15 plus 25 plus 35 plus 45 and divide it by 5 terms. However, each time for the daily commute is happening a different amount of time. So for 5 minutes of my commute, 4 employees are taking that long. So I need to have 5 minutes times 4 employees, plus 15 minutes times 9 employees, plus 25 minutes for 6 employees, 35 minutes for 4 employees, and 45 minutes for 2 employees. Divided by, now our number of terms is not just 5 here. How many different employees are there? So 4 plus 9 plus 6 is 19, plus 4 is 23, plus 2 is 25. So there's actually a total of 25 employees here. That's what we're going to be dividing by. Standard deviation follows the exact same now. We just need to keep in mind the number of employees we need to be multiplying by. So standard deviation equals the square root. So our number where we have 5, again, we need to multiply 4 times this happens. So 5 minus our average, which we didn't finish here, sorry, is 21.4. So back to here, 5 minus 21.4 squared plus 9 times 9 different employees take 15 minutes. So minus, how far away is that from the average? And we'll square it. Plus 6 times 25 minus 21.4, and we'll square that. Plus 4 times 35 minus 21.4, and we'll square that. Plus 2 times 45 minus 21.4, and we'll square that. Again, drag your square root sign so that we know that covers everything. And it's all divided by 25. Simplifying up top, we have 4 times 268.96 plus 9 times 40.96 plus 6 times 12.96 plus 4 times 184.96 plus 2 times 556.96. All divided by 25. So you can finish the rest of that in your calculator, just simplifying, but you should get down that it's going to be the square root of 135.04, which in the end gives us a standard deviation of 11.62. So again, into comparison with the first 2 examples, this standard deviation is much larger than the others, which tells us that the distance between our numbers to our mean is a lot larger than the distance it was from the first 2 examples. Last example here. So again, we're given a range. Our first step we want to do is identify what would that middle number be. What's in between 10 and 12? So the numbers we'll be using is 11, 14, 17, and 20. And we need to remember to multiply them by the number of days that that number of orders occurs. So there's 11 orders, 4 different days. There's 14 orders, 12 different days, and so on. So when we're identifying what our mean is, we want to make sure that we are multiplying that each time. So our mean would be 4 times 11 plus 12 times 14 plus 20 times 17 plus 14 times 20, all divided by 4 plus 12 is 16, plus 20 is 36, plus 14 is 50. What I'm going to show you in this example is write down some steps for how you can actually determine all of this and skip that big long formula. The instance where this is helpful is we want to make sure we understand the formula if I'm asking you to show your work. But if you're given a lot of data and it takes a lot of time to write out all of this, the deviations, the sum of all the deviations, you can actually use your graphing calculators to determine this quite quickly. So I'm going to write down some steps. On your calculator, if you have a stat button, I want you to find that. And if you have any troubles with this, please come to the back and ask me to show you these steps. So you want your stat button, and you want to edit that by pressing 1. You'll have a few lists come up, list 1 and list 2, and that's where you're just going to enter your data from the chart. So the data in order in list 1 is right here. You're going to type in 11, 14, 17, and 20. And the numbers you'll type into list 2 is 4, 12, 20, and 14. You'll be able to calculate if you click 1 VAR and then your stats list 1 and list 2. We'll calculate everything you need to know. A list will show up and it'll tell you what your mean is. It might show you the X with the line, or it might have the fancy U. And you'll see that's 16.64. It'll also give you the symbol standard deviation with an X, or some calculators are just the standard deviation, but your calculator will solve that that's 2.73. You can answer this using your graphing calculator by using your stat and entering in all of your information into your lists. That being said, this question is just as solvable using the formula if you prefer to do that, but you can always use one or the other and double check with the option you didn't choose. Your assignment is on page 233, number 1 to 4 all. Come to the back if you have any questions.